Welcome to this lecture on the fundamentals of biomolecules. Today, we are going to explore a very specific and fascinating topic: reducing and non-reducing sugars. If you have ever wondered why a seared steak turns brown, or how doctors historically tested for diabetes, the answer lies entirely in the microscopic structure of these sugars. We will build your understanding from the ground up. So, let us dive right in. Before we look at complex chemical structures, let us start with a simple analogy. Imagine you are at a busy networking event. Your goal is to shake hands with as many new people as possible. To do this, you need at least one free hand. If you are carrying a heavy box and both hands are tied up, you simply cannot interact. In the microscopic world, sugars behave exactly the same way. Some sugars have a free hand, allowing them to easily interact and transfer electrons to other molecules. Others have their hands tied up, making them completely unreactive. Now that we understand the networking analogy, let us look at the formal scientific definition. A reducing sugar is any carbohydrate that acts as a reducing agent because it possesses a free aldehyde or ketone group. This is the chemical equivalent of our free hand. In their cyclic ring forms, these reactive sugars contain a specific functional group known as a hemiacetal or hemiketal. Because of this specific grouping, the sugar ring can easily open up in a water solution to reveal a highly reactive chain. All simple sugars, or monosaccharides, fall into this category. Having seen what makes a sugar reactive, we must now ask what makes one unreactive. A non-reducing sugar does not have a free aldehyde or ketone group. Instead, its reactive center, which we call the anomeric carbon, is permanently locked in a glycosidic bond. Going back to our analogy, this sugar is holding a heavy box. Its hands are tied. Because the reactive centers are bonded tightly together, the ring cannot open up in solution, and it cannot donate electrons to other molecules. Common table sugar, known as sucrose, is the classic example of this locked state. To truly grasp how this works, let us look at the chemical formula for this process. This equation represents the cyclic hemiacetal form of a sugar opening up. The double arrows indicate that the sugar exists in a dynamic equilibrium with its open chain form when dissolved in water. When the ring opens, it produces a free aldehyde group, represented by R'-CHO. This exposed aldehyde is what makes the sugar a reducing agent. If the concentration of the hemiacetal increases, more free aldehyde is produced, increasing the sugar's ability to reduce other substances. Before we move on, let us see this with a concrete example from the laboratory. You are given maltose, a disaccharide formed by two glucose molecules linked at carbons 1 and 4. We need to determine if it is a reducing sugar. Our approach is to check for a free anomeric carbon. Because the linkage only uses carbon 1 of the first glucose and carbon 4 of the second, the anomeric carbon at position 1 of the second glucose remains completely free. Therefore, we conclude that maltose is indeed a reducing sugar, capable of donating electrons. So we have established that maltose is a reducing sugar. Let us break down exactly why this happens chemically. We start by identifying the functional group at that free carbon 1 position. Because it is not locked in a bond, it forms a hemiacetal structure. As we saw in our earlier formula, when this hemiacetal is placed in an aqueous solution, it undergoes dynamic equilibrium. The ring spontaneously opens up, exposing the reactive aldehyde group. This step-by-step structural feature is the fundamental reason why maltose can act as a powerful reducing agent in chemical reactions. Now that we have seen a reactive structure, let us look at the formula for an unreactive one. This formula represents an acetal structure, which forms when two anomeric carbons bond together. The variables R, R prime, R double prime, and R triple prime represent the various parts of the connected sugar rings. The most crucial feature here is the central carbon. Notice that there is no free hydroxyl group attached to it. Because this structure is completely locked, increasing the amount of this sugar in water will never result in an open chain or a free aldehyde. Let us apply this new formula to another laboratory example. You are given sucrose, which is formed by a glucose and a fructose molecule. We must determine its reactivity. We look at the linkage and find that these two molecules are linked exactly at their respective anomeric carbons. This means both reactive centers are tied up in the glycosidic bond. Because neither carbon is free, we can definitively conclude that sucrose is a non-reducing sugar. It can't interact with or reduce other molecules under normal conditions. Following our conclusion about sucrose, let us prove why it remains unreactive. When we observe the specific bond between carbon 1 of glucose and carbon 2 of fructose, we see that this dual linkage creates the full acetal structure we just discussed. The mathematical and chemical reality of an acetal is that without a free hydroxyl group on the anomeric carbon, the ring is physically incapable of opening. Because the ring cannot open, no aldehyde or ketone can ever be formed in solution, proving exactly why sucrose cannot donate electrons. To solidify everything we have discussed, let us look at this structural diagram. On the left, you see the molecule of maltose. Notice the red circle highlighting the free anomeric carbon on the far right. This is the hemiacetal group that can open up. On the right, you see sucrose. The blue arrow points directly to the center where the two rings are joined. Both anomeric carbons are locked together in that central bond. This visual perfectly captures the fundamental difference between a sugar that can react and one that cannot. Now that we understand the molecular structures, why do we care about this in the real world? This concept is incredibly important in both medicine and food science. Historically, doctors used the reducing property of glucose to test for diabetes by checking a patient's urine. In the food industry, reducing sugars are directly responsible for the Maillard reaction. This is the complex chemical process that gives browned foods like baked bread and seared steaks their delicious flavor. Non-reducing sugars, like sucrose, will not undergo this browning easily unless they are broken down first. To understand how the diabetes test works, we must look at the chemical equation for Benedict's reagent. This formula shows the reducing sugar, represented by RCHO, reacting with blue copper 2+ ions in an alkaline solution. When the sugar reacts, it is oxidized into a carboxylic acid, while the copper ions are reduced to form copper 1 oxide, which is a solid red precipitate. If the concentration of the reducing sugar in the sample increases, the amount of red precipitate also increases proportionally, allowing us to measure the sugar levels. Let us zoom in on the most critical part of that previous reaction, the core electron transfer. This simple formula captures the essence of what a reducing sugar actually does. The copper 2+ ion acts as an electron acceptor. The reducing sugar provides the electron, represented by E-. When the copper ion gains this electron, its physical state changes entirely, reducing down to a copper 1 plus ion. This single transfer of an electron is what drives the dramatic physical color change from a clear blue liquid to a cloudy red mixture. Let us apply these formulas to a real clinical scenario. A medical student adds 5 milliliters of Benedict's reagent to 2 milliliters of a patient's urine and heats it. The solution turns from a clear blue liquid to a brick red cloudy mixture. We are asked what this indicates. Because we know Benedict's reagent changes color when reduced, this observation tells us that an electron transfer has occurred. The final conclusion is that the patient's urine contains a high level of a reducing sugar, most likely glucose, which is a major diagnostic clue for diabetes. To complete our understanding of this clinical test, let us trace the exact chemical reasoning behind the color change. We start with the fact that glucose in the urine has a free aldehyde group. As the mixture is heated, this aldehyde oxidizes into a carboxylic acid. In doing so, it must shed electrons, which are immediately accepted by the blue copper 2 plus ions. This forces the copper into its reduced state, which rapidly precipitates out of solution as red copper 1 oxide. This proves exactly how a microscopic structural feature creates a visible, life-saving diagnostic result. We have covered a lot of ground today, so let us summarize the key takeaways. First, the entire distinction comes down to the availability of a free anomeric carbon. If it is free, the sugar is reducing. If it is locked in a bond, like in sucrose, it is non-reducing. Second, this microscopic structural difference dictates how carbohydrates behave in everyday chemical reactions. Understanding this is the key to mastering biomolecules, whether you are studying human metabolism, diagnosing diseases, or even cooking a meal. Great job following along with these complex concepts.